A model that was 94% accurate when you deployed it is now 71%. Nobody touched it. Nobody changed the code. The data pipeline is clean. What happened is that the world moved and your model did not. That is model drift. A machine learning model learns patterns from historical data. It extracts relationships. If X, then probably Y. Once deployed, it makes predictions against new incoming data. Model drift is what happens when those learned patterns stop accurately describing reality. There are two distinct mechanisms. The first is data drift, sometimes called covariate shift. The inputs to your model are changing. The feature distributions are shifting. Your fraud model was trained on 2022 transaction patterns. In 2025, transaction volumes, amounts, and merchant categories look different. The model is applying old rules to a new world. The second is concept drift. The relationship between the input and the outcome has changed. A credit scoring model trained before 2020 learned that certain employment patterns predicted repayment. Post-COVID, remote work, gig economy income, and career breaks look different in the data. The same features now carry different predictive weight. The relationship itself changed. 3 examples from production systems. In fraud detection, fraud patterns change because fraudsters adapt. A model trained to flag anomalies in transaction sequences becomes progressively less effective as fraud rings adopt the patterns the model learned were safe. This is adversarial concept drift. The ground truth is being actively moved by the adversary. Fraud detection models experience significant performance degradation within 6 to 18 months without retraining. In recommendation systems, user preferences shift. A product recommendation model trained on pre-pandemic behavior will over-index on travel and dining and underserve home goods and digital entertainment when behavior patterns change. The model is not wrong about the past. It is wrong about now. In credit scoring, macroeconomic conditions restructure the feature importance hierarchy. Employment stability signals that predicted repayment in a low-rate environment carry different weight when rates are at 20-year highs. Debt service ratios look structurally different. Not all models drift at the same rate. 5 categories face structurally higher exposure. Financial models, credit scoring, fraud detection, and risk models operate in environments where the underlying behavior is adversarially adaptive or macroeconomically sensitive. Recommendation systems are consumer behavior models. Consumer behavior is one of the fastest changing distributions in production. NLP models trained on corpus data from a specific period will misclassify evolving terminology and domain-specific shifts. Time series and forecasting models are anchored to historical patterns. Structural breaks are permanent shifts in the data-generating process, invisible to a model that has only seen the pre-break regime. Healthcare and clinical prediction models. Population health data shifts with demographic change, treatment protocol evolution, and disease prevalence. Measurement falls into three categories: input monitoring, output monitoring, performance monitoring. Input monitoring tracks the distribution of features going into the model. The standard metric is Population Stability Index. Psi below indicates negligible shift. Between and indicates moderate shift requiring investigation. Above indicates significant shift. Your model is now seeing inputs it was not trained on. For numerical features, Kullback-Leibler divergence and Jensen-Shannon divergence quantify distribution distance between training and production data. Jensen-Shannon is bounded between 0 and 1 and is symmetric, which makes it easier to threshold. Output monitoring tracks prediction distribution. If your model suddenly predicts fraud 3 times more often than its baseline rate, something changed. This is the most actionable signal because it is directly visible to downstream systems. Performance monitoring requires ground truth labels, which creates the delayed label problem. In fraud detection, labels arrive 1 to 6 months after the initial prediction. You have a blind period where the model may be deteriorating, but you cannot measure it directly. Shadow models address the blind period. You run a retrained challenger model in parallel, logging its predictions without acting on them. When labels arrive, you score both models against the same outcomes. 4 approaches in increasing order of cost and disruption. 1. Scheduled retraining. Retrain on a fixed cadence using a rolling window of recent data. Simplest operationally. The risk: you retrain on schedule even when drift is low and fail to retrain fast enough when drift is high. 2. Triggered retraining. Drift detection metrics cross a threshold, and an automated pipeline initiates retraining, validation, and staged deployment. Lead time from trigger to production deployment is typically 2 to 6 weeks. 3. Online learning. The model updates incrementally as new data arrives. Appropriate for models where drift is continuous and fast-moving, such as real-time fraud detection. The operational complexity is higher. You need rollback capability because online updates can introduce instability. 4. Architectural change. Sometimes drift reveals that the model class is wrong for the problem. A static model in a non-stationary environment eventually requires replacing the architecture, not just retraining it. This is the most disruptive path and the most expensive. Time and cost vary by model complexity, regulatory environment, and infrastructure maturity. For a moderately complex model with established ML ops infrastructure, 2 to 6 weeks from trigger to deployment. The cost ranges from $10,000 to $50,000 per retraining iteration. Compute drives 70 to 80% of that total. For regulated industries, the timeline extends. Financial services firms must document that model updates maintain appropriate risk controls. The regulatory review layer adds weeks to months on top of the technical timeline. Annual model maintenance costs run from $20,000 to $150,000 per model, depending on complexity and retraining frequency. A 5-year ML Ops implementation adds $60,000 to $95,000 for monitoring infrastructure. One path that has become viable, fine-tuning with LoRa adapters. For large language models and NLP models, fine-tuning costs $2,000 to $15,000. You are updating a small number of parameters rather than retraining the full model. The calculation that most teams miss is not the cost of retraining. It is the cost of not retraining. A fraud model running at 71% accuracy instead of 94% is not a technical problem. It is a financial exposure problem. Model drift is not a failure state. It is the natural consequence of deploying a model into a world that continues to move after the training cutoff. The question is not whether your model will drift. It will. The question is whether you have the measurement infrastructure to detect it before the degradation becomes a business problem, and whether you have the retraining pipeline to respond before that degradation propagates into decisions. The models that organizations trust most tend to have the least monitoring. The ones embedded deepest in operations are the ones with the longest gap between last validation and today.